Hey guys, good afternoon. It's Thursday, and we're going to be talking about section 5.7, inverse and radical functions. Our specific goal today is to talk about how do you find the inverse of an invertible polynomial function, and how do we restrict the domain to find the inverse of a polynomial function. So there's two big parts there. How do we find a polynomial function's inverse, and then how to restrict domains to get inverses of functions that didn't have an inverse before. It's important to note, as we'll be discussing here shortly, some functions have an inverse and some don't. But just because it doesn't have an inverse doesn't mean we can't make one work. First thing we're going to talk about is the definition. Now, the book doesn't make this very clear, but the definition is actually contained right here. The definition of an inverse function. There's actually a couple different versions of this, and so I want to go through each one as we get to it. So what does it mean to be an inverse function? Well, notice they define two functions, f and g. So, what does it say? These two functions are considered inverses if you look at the function f and it has the point a, b. Then g has the point b, a. Or, as the book states, in other words, the coordinate pairs of the inverse functions have the input and output interchanged. That's a big detail, meaning in f I plug in a and get out b. So let's say a and b are like 3 and 7. So let's say I plug in 3 and I pop out 7. Well, then g is going to have me plug in 7 and it will pop out 3. Now, what this doesn't tell me is, well, what if I plug in 3 into g? It doesn't say anything about that. All it says is that if 3 gets me 7f, then 7 has to give me 3 in g. This is the definition of an inverse, meaning the inputs and outputs are interchanged. Meaning the input of one, like 3, is the output of the other, 3. So, inputs and outputs are interchanged. That's the primary definition. There is a secondary definition farther down, but before I do that, let's note a couple of different restrictions, because there are a few restrictions on this. First restriction. Only one-to-one functions have an inverse. Straight out of the text. Only one-to-one functions have an inverse. Well, what's that really mean? A one-to-one function, you'll remember, has two parts to it. Every input has a unique output, and it has to pass the horizontal line test. Meaning, this function does not have an inverse. The parabola does not have an inverse because it doesn't pass the horizontal line test. Remember, horizontal line test, it has to strike only one place. If it strikes in two places, it's wrong. Whereas something like this function, this has an inverse. It's actually a cubic function. And so you'll find that some functions just don't naturally have an inverse, whereas some functions always have an inverse. Now here's the thing. Just because it doesn't have an inverse now doesn't mean we can't force it to have an inverse by restricting the domain. That's what this piece is about and what we're going to finish with today. So let's go ahead and look at the other definition for an inverse function. It's actually right here. The other definition of an inverse function. Again, I'm still using f and g. If I plug g into f, or f into g, I get the same solution. In other words, if I take f and plug it into g, only x will remain. Any constants, any powers will all cancel out through algebraic operations. In other words, everything will cancel. If you plug f into g, everything will cancel. If you plug g into f, everything will cancel. Now, last of all these, if f is a function, it is typical to notate f to the negative first as the inverse. So, you'll often see f and f inverse related in much the same way as f and g here. So in this case, if we follow this same property, this would mean that f inverse of f equals x, and f of f inverse equals x. Let's look at some examples, because I think it's important to see these in terms of realistic functions before we really do anything else. And so, sadly, there's no real questions in your homework that ask you to do this, so I'm actually going to use example 1 here very heavily. Example 1 claims that these two are inverse functions, and it shows how they are by testing these two properties that we just talked about. It tests the first one by taking the f function and plugging it into the inverse. So it takes the f function, 1 over x plus 2, and plugs it into the f inverse function, meaning everywhere in the f inverse there used to be an x, it replaces it with the inverse function, and shows that everything cancels out. The fraction ends up canceling, becoming x plus 1 minus 1, and then the 1's cancel, leaving just x by itself. And down here, same thing happens. So we plug in f inverse into f, and everything just cancels out. The 1 and the negative 1 end up canceling, leaving this fraction, and the fraction cancels, leaving just x. This is how we define an inverse. You can see here a different inverse, and I will showcase this one to illustrate exactly what an inverse function does by showing, how to prove it's an inverse. There's no questions in your homework that ask you to prove, but I think it's important to see it, and so I'm making sure it gets in here. So my two functions are f of x is equal to x plus 5 over 3, and my f inverse, it claims, is 3x minus 5. Let's note here for a second that many of the pieces are still here, right? You have 5 and 5, it's just one's positive and one's negative. You also have 3 and 3. Notice that one's being multiplied and one's being divided. Now, they're not being multiplied to the same thing or divided to the same thing, right? It's not 1/3 x, it's x plus 5 over 3. And so the 3 is being applied to everything. And so it doesn't always match up piece by piece. But notice that everything is accounted for. There's a 3 and a 3. There's a 5 and a 5. They switch forms, but they are there. So let's verify. How do we verify? We're going to perform two tests. We're going to take f inverse and plug f into it. And then afterwards, we're going to take f and plug in f inverse. This is a test you can always perform to see if they are in fact inverse functions. Because if this is correct, when I'm done, I should get x by itself. Well, let's test this out. My f inverse function is 3x minus 5. So 3x minus 5. But everywhere there's an x, I'm going to replace with f of x. So x plus 5 over 3. Remember, what this operation means is everywhere there used to be an x in f inverse, I'm going to replace it with the entire f of x function. So everywhere there used to be an x, I replace with f of x. Notice that if I do that, the function actually simplifies down to x. The 3 and the 3 are going to cancel, leaving x plus 5 minus 5. Now the plus 5 is inside parentheses, but the parentheses aren't doing anything, so we can just drop those. Positive and 5, negative 5 will cancel, leaving just x. Notice that if we do the exact same test down here, the same thing happens. We take our f function, and we plug in f inverse, meaning everywhere in the f function there is an x. We're going to replace it with f inverse. So we take the f function, which is x plus 5, And everywhere there used to be an x, we're going to replace with 3x minus 5. And just like before, everything's going to cancel. So the 5 and the negative 5 are going to cancel because the parentheses aren't doing anything. So we end up with 3x over 3. The 3 on top and the 3 on bottom are going to cancel. And when they do, we're left with just x by itself, exactly as we predicted. Which means that these two are inverses. If we look back at the very first problem they show in the text, these are also inverses. More complicated inverses, but they are. Here they are. Here are these two. And to illustrate this, I'm going to show that these are inverses by plugging into each other. Note, just like before, everything in the first equation is contained in the second equation. So there's a 2 and a 3 as numbers. There's a 2 and a 3. They're not in the same location. They're not done in the same way, but they're here. There's a pi in this equation. Well, there's a pi in this equation. There's something being cubed. Notice there's something being cube rooted. This is a common trait among inverses, is they just take the operations and invert them as well in sometimes unpredictable ways. So instead of multiplying by 2 and dividing by 3, notice it's multiplying by 3 and dividing by 2. Notice instead of cubing the variable, I am cube rooting something. Well, let's showcase that these are in fact inverse functions. So I'm going to show that v equals 2/3 pi r cubed and r equals the cube root of 3v over 2 pi. I'm going to show that these two are inverses. Well, how do I do that? Well, what I can do is I can plug one into the other. Meaning I take my 2/3 pi r cubed, and everywhere there used to be an r, I'm going to plug in this function, which is the cube root of 3v over 2 pi. And I can do the same thing down here. I can take this function, which is the cube root of 3v over 2 pi, and I can plug in the other function, which is 2/3 pi r cubed. And if this is done correctly, each of these is going to simplify down to just a variable. So we take these. The cube and the cube root are going to cancel, leaving 2/3 pi times 3v over 2 pi. Well, remember, a 2 on top and a 2 on bottom can cancel. A 3 on top and a 3 on bottom can cancel. A pi on top and a pi on bottom can cancel, leaving just v. And in this one, the same basic thing happens. So the 3 times this, we have a 3 on top and a 3 on bottom. So we end up with the cube root of 2 pi r cubed over 2 pi. We then have a 2 on top and a 2 on bottom, a pi on top and a pi on bottom, meaning we're left with the cube root of r cubed. And then, of course, we know cubes and cube roots cancel, leaving just r. Notice that no matter which way we did it, all we're left with is the variable. Now notice for this example, it has different variables. That's because in the problem, it has different variables. This is actually pretty common. And so when we're finished, we should only end up with the variable left. Everything else should cancel and disappear. Okay, so now we know what an inverse is. So the next question becomes, well, how do you find an inverse? Well, here's the how-to. Let's do it. How do we determine what an inverse function is? It says replace f of x with y, interchange x and y, and then solve for y. I think that's a little wordy. I like to show it. So instead, let's look at number 12 and number 20. Go into my homework now. Most of your homework problems tonight specifically ask you to be able to find the inverse function. So make sure you can do that. So I come over here. Let's look at 12. It says we have f of x is equal to x cubed plus 5. Well, how do we find the inverse? Well, let's add to my notes. to find an inverse. I recommend, much like the book does, we swap our x and y's. So in other words, remember, by our definitions, we are swapping inputs and outputs. So remember, this was our definition, right? Inputs and outputs are interchangeable. And so what do? Well, we just interchange them. We swap them. Once we swap them, so usually this is already solved for y. Right? That's how most functions are. And if it's not solved for y, it's solved for, f of x. So what we're going to do is we're going to swap x for y, and then we're going to solve for y again. And this will be our inverse function. Let's look at an example. So, according to the text, what it recommends doing is we think of f of x not as f of x, but as y. For many of you, that may be a very comfortable step. You may not like f of x very much, but that's okay. Okay, so step one. What is the first thing we're going to do? We're going to swap x and y. I mean, everywhere there's an x, we're going to replace it with y. Everywhere there's a y, we're going to replace it with x. So this becomes x equals y cubed plus 5. So notice it's the same function that we started with, but just everywhere there used to be an x is now a y. Everywhere there used to be a y is now an x. And now, step 2, once we swap them, we're going to solve for y. So I want to get y by itself. I need to go through the algebraic steps to get y by itself, which means for this problem, I would subtract 5. I get x minus 5 equals y cubed. I want to get y by itself. Y is not by itself. It's been cubed, so I use a cube root. When I use that cube root, I end up with y by itself equals the cube root of x minus 5. And this is our f inverse. Notice how we just take our function, swap around the x and the y, solve for y algebraically, and then that becomes our inverse function. And just to showcase the point, I can prove this is the inverse by plugging it back in, which I will do down here below. This is not something you're required to do in your homework, but I want to make sure this is actually right. If this is correct, then if I take x cubed plus 5, and I plug in the cube root of x minus 5, I should end up with x, which I do. The cube and the cube root cancel, leaving x minus 5 plus 5. And then x minus 5 plus 5 is x, so I know it works. And it should always work both ways. So if I do the cube root of x minus 5, I should be able to plug in x cubed plus 5 and get the same answer. So negative 5 and positive 5 are going to cancel. We end up with the cube root of x cubed. Cube root and cube root cancels, leaving just x by itself. So I know it works. This is the inverse function. Let's compare this to number 20. It's the same basic methods. Note there's going to be a lot of algebra heavy parts today. Okay, number 20. We have f of x is equal to 9 plus 2 cube root of x. Okay, let's do it. We're going to find the inverse. So, step 1. Once we rewrite in terms of y equals 9 plus 2 cube root of x, we're now going to swap x and y. meaning everywhere there used to be an x, I'm going to replace with y, and everywhere there used to be a y, I'm going to replace with x. 9 plus 2 cube root of y. And now we're going to take our time, and we're going to solve for y. Let's do it. To get y by itself, I have to move the 9, the 2, and the cube root. I make sure to follow correct algebraic procedures. I would move the 9 first. So it becomes x minus 9 equals 2 cube root of y. So what I did was I subtracted 9 from both sides. So minus 9 and minus 9. Next thing I would do is I'm going to divide both sides by 2. So I get x minus 9 over 2 equals the cube root of y. So I just took both sides and divided by 2. And then lastly, I want to get y by itself, so I cube both sides. So I get x minus 9 over 2 cubed equals y, because I simply cubed both sides. And so this is our inverse function. So f inverse of x is equal to x minus 9 over 2 cubed. Note that this function, just like before, contains all the same pieces. There's still a 9, it's just being subtracted instead of added. There's still a 2, instead of being multiplied, it's being divided. There's still a power of 3, but instead of being in a root, it's actually on the outside as a power by itself. And so everything in the original problem is contained in the inverse, just in a different way, usually in the inverted way. So instead of adding 9, we subtract 9. Instead of multiplying by 2, we divide 2. Instead of doing a root, we do a power. It's just sometimes it's unpredictable how this can be fitting together. At this point, I want to now take both of these equations, which I just got, and showcase what these look like on a graph. Because the next part of our notes deals with what does the graph of these functions look like. So next part of our notes. So what you want to do is you want to graph our f of x function. You want to graph the inverse function. And there's one more function I want you to graph. It is the basic function y equals x. Now I'm going to show this once on Desmos and once without Desmos using a standard calculator, just to showcase how these kind of fit. Okay, here's Desmos. In my Desmos, I'm going to graph 3 things for each of these problems. I'm going to graph the original function, what I think is the inverse function, and I'm also going to graph y equals x. That last one will become more apparent when we finish, about why it's so useful. Let's look at 12. 12 didn't ask us to graph, but a few of our questions in our homework do ask us to graph. So let's make sure we can do both. Now, in Desmos, what I do is I type in my first function. My first function is x to the third plus 5. There's my graph. And then what I'm also going to graph is my inverse, which I have as x minus 5. And it's a cube root, so that means it's a 1/3 power. Now, real quick, what do you notice about both these functions? Hopefully, what you notice is this idea that they look very similar. It looks like as if one is just a slightly changed version. Like it almost looks like they're turned, but they're not, right? Because if you look at this function, it starts slow, curves into the middle, kind of has a stopping place, and then comes back up. Where this one kind of almost does the opposite. But I do want to point out here a few of the properties we've already discussed. Right? For every a, b, there is a b, a. So look here. In red, I have the point 0, 5. But in blue, I have the point 5, 0. In blue, I have the point 6, 1. And in red, I'll have the point 1, 6. So this property holds naturally. It has to always have this property, this idea, where every single AB in the original function has a BA in the inverse. So if I look over here, even weird ones, like let's go with this one, sure. So this one looks like negative 1, 4. That means on my graph of the other one, I should have the inverted version of that. So instead of 1, 4, I should have the point 4, 1, or 4, negative 1, which I do, 4, negative 1. Now, the reason why I tell you to graph the last line, because I think that last line is so very important, is because there's a relationship that we're missing if we're not paying careful attention. Notice that the inverse is just a reflection across this line. You can always put this third line in and see that they match across this line, right? There's 0, 5, there's 5, 0, right? Here's 0, negative 1.71, here's negative 1.710, right? They have this natural relationship. They always have this piece that fits together this way. And so this little green line here, this third line, is not a requirement in your homework when it says to graph these. But it is helpful to see that it is an inverse. Because if you make a mistake on here, let's say you do your math wrong and get plus 5. Oh. So you do that wrong and get plus 5. They still look sort of inverses, but it's much harder to tell that it's wrong because you're missing that middle line. And so having that middle line, and ask yourself, hey, does this actually break this into two graphs that are on each side? Well, no. We must have made an algebraic mistake. And so it's a way to check your answers. This third line should always split your graph directly down the middle. And that's a really big detail there. Then notice it does it for 12, and it will also do it for number 20. So if I go to number 20, I can do the exact same thing. I'm going to come in here and replace this one with my original function, which was 9 plus 2 x to the 1/3 power. And this one was parentheses x minus 9 divided by 2. And all of this is to the 3rd power. Like, it's a little hard to tell, but yep, those are inverses. And you can clearly see how they have this nice reciprocal relationship, right? This has the 0.90. This has the 0.09. If we go like to another easy value, I think that's actually it. Oh, that's not a nice one. Okay, and then of course there's sometimes a place where they cross, and that's the only place where they're the same inputs and outputs. But again, it always follows this rule. This rule of AB becomes BA, you know? 0, 9 becomes 9, 0. It has to, because it's an inverse. Alright, so that's the first part. And that's a good piece of your homework too. But there's a second part. And this has to do, if you look in your homework, you'll notice that some of these problems have some restrictions on them. And so let's talk about those. Okay. Notice that for some of these problems, like number 5, the first problem you have, it states a restriction here, 4 to infinity. The reason being is this function does not actually have an inverse. If I was to graph this function, which I will do now, the function was x minus 4 to the second. This function fails the vertical line test. Okay, it just fails it. It doesn't work with a vertical line test. So what I can do is I can restrict this to just that piece. Wait, hold on. I gotta remember how Desmos does it. I think it's semicolon x greater than or equal to 4. 1 second. All right, kids, what do you do if you don't remember how to do something? Look it up. Piecewise functions in Desmos. Remember, these are called piecewise because we're only doing a piece of the function. We are only doing from 4 to infinity. So we're only doing a piece of the overall function. So this is called a piecewise function. So how do we do it? Well, we do, looks like the boundary first, colon, and then the equation. So I'm going to do that. It says the boundary first, and it says do a colon, and then I got to put it in curly braces. Nope, square braces, curly braces. There it is. Notice that this function, compared to the original, not invertible. This function, invertible. The original function fails the horizontal line test, right? You know, at this dot, there's two different answers that give me that dot. You know, here, 0, 16 and 8, 16. That's not allowed if I want to pass the horizontal line test. Remember, the horizontal line test says I can only have one time I cut through the graph if I cut it left to right. But in this case, I cut it twice. So this one doesn't have an inverse, but this one does. And so, how do I do this? Well, let's go back to our notes. Okay. So how do we deal with these inverses? Well, it helps if we understand the domains of these inverse functions. And let's go to right here. Here we go. Okay. It's important to note, if the function is not one-to-one, and common functions that are not one-to-one are even-powered functions. So you will be forced to do this if your function is even-powered. If the function is even-powered, we restrict the domain of the function so that it becomes one-to-one, thus creating a new function that will have an inverse. So we have to be willing to restrict the domain. How do we do that? Here we go. We have to first figure out when will this function be one-to-one. And so it helps to figure out what places this function splits apart. In this case, it showcases these two examples as places where we could split this thing apart and get two pieces. Notice the exact same graph that we have for our function. Right? Exact same graph. It's just they're only focusing on either the right side or the left side. And so it's basically taking this problem and splitting it into a left-hand piece and a right-hand piece, which, according to the book, we are very much allowed to do. Because remember, the original function, just the x minus 4 squared, is not invertible because it fails that horizontal line test. So it splits it into two pieces that are invertible. Okay, now from here, we can find the invertible functions by doing the same thing we did before. We can interchange x and y, meaning everywhere there used to be an x, we replace with y. Everywhere there used to be a y, we replace with x. And then we solve for the equation. Notice that because it's even, there will often be a plus or minus, because remember, when you take a square root or a fourth root or sixth root, any even roots will always end up having a plus or minus in them. One of these functions will be the inverse, but only one of them. So let's take a look at our next example. Let's take a look at 16. Okay. So, on 16, we have the following function. We have fx is equal to the square root of 2x plus 1. Well, let's find the inverse. So, to find f inverse of x, we're going to follow through on our previous steps. So we're going to take our original equation. We're we're going to rewrite using y. We are then, everywhere there used to be an x, we're going to switch with y. Everywhere there used to be a y, we're going to switch with x. Meaning I end up with this new equation. X equals the square root of 2y plus 1. And now I solve for y. So in this case, I'm going to start by square both sides. So that means I'm going to get x squared over here. And I'm going to end up with 2y plus 1 over here. I'm then going to subtract 1. From both sides, meaning I get x squared minus 1 equals 2y. And then I'm going to, of course, divide both sides by 2, giving me our final equation as x squared minus 1 over 2 equals y, meaning my f inverse is x squared minus 1 over 2. Now, here's the issue. When you graph these are not inverse functions, because this one is actually not invertible. Remember, the definition of inverse is it has to work both ways. Meaning this function is actually not quite correct. There's a domain problem. Take a look. If I pull up my graph again, and I type in these two functions, my first function is the square root. See, I think it is square root of 2x plus 1. And then if I type in x squared minus 1 over 2. Notice that this purple function is too big. It will not flip across that line, y equals x. Part of it will, but this green one stops right here at negative 1/2, 0, which means we should have this purple one also stop in a similar location at negative 1/2, or 0, negative 1/2, here. How do we get this thing to stop? Well, it turns out, in this function, the domain restriction is x has to be greater than or equal to 0. Because if you look at this function, if x is greater than or equal to 0, then this function would be an inverse. So if I take this function, define it using my curly brackets, x greater than or equal to 0, colon. Notice these are clearly inverses of each other. They have that relationship where they are matching components. And so, if I restrict this domain, then I can get it to work. So the question is, how do we get that domain restriction? And in this case, the easiest way is to use the vertex. Now, we talked a little while back about how to find the vertex of a function. It involves a couple steps, but it can be done. And for these problems, the vertex is really helpful for figuring out which piece will allow us to fix that domain. So let's take a look. Pulling out my notes. Okay. So, last piece we have today is domain issues. Okay. So, these are common in two situations. These are common with even powers and roots. You have to be very careful with both of these because there's a good chance it's going to have a domain issue. So how do we do it? Well, if no matter which one you're given, you'll eventually do the same process. I recommend, in both cases, start with the even. So find the inverse by the same process, but then of the two powers, of the two pieces, choose the one that is the even one, because that's the one we're going to be testing it with. So like on 16, notice we restrict the domain on this one, not the other one. Okay? This is the one we restrict. This is the one we might have to choose, but this is the one we restrict. Okay, part B. With even, we're going to find the inverse. Or not the inverse. I blame my brain. Find the vertex. Now I recommend doing this with a graph, but you can also do it with a formula. And I'll go through examples of each here in a second. This number 16 was one where I did it with the graph. So notice how this 0, if I look at my graph, the 0 was the bottom of this fraction. So if I get rid of this piece, right, the 0 was the bottom of this parabola. And so how did I fix that? Well, we just undid the two pieces by only choosing one of them. So we split it into a left piece and a right piece, and then we choose the piece that corresponds to the part we actually want that is the inverse. If I had chosen the other piece, instead of doing greater than, I had done less than, it is also not an inverse, because again, it's not over that line. And so notice how those are my two options. I can choose this one, or I can choose this one. And of these two, only one of them is right. This one is the wrong one. And so we take this answer that we got, and we look at it as two answers. Notice how we split it apart was at 0, where the actual picture splits into a left-hand side and a right-hand side. So that's the easiest way, is to look at the graph. On some of them, though, there's somewhere you may want to use the formula instead. It's the same basic process, though. Okay, let's do another example. So now let's take a look at number 22. 22. Let's look at 7. No, that's 8. 8. We'll do 22 in a second. 8. So you have to make sure that when you have multiple possible solutions or a possible domain error to check. Always check. And so in number 8, we have the following function. F of x is equal to 3x squared plus 5. And notice that in this case, they've told us to use the very specific component, negative infinity to 0, for this graph. Which means that our inverse is probably going to also be restricted in some way. So let's look at what we do. So step 1, we're going to write it as y equals 3x squared plus 5. Step 2, we're going to rewrite as x equals 3y squared plus 5. And now we're going to solve for y. Step 3, so I took the original function, rewrote it, then I took that function and switched around the variables, and now I'm solving. So to do that, I'm going to subtract 5. So I do minus 5 and minus 5. That'll give me x minus 5 equals 3y squared. I'm then going to divide both sides by 3. Give me my new equation, x minus 5 over 3 equals y squared. I'm then going to take a square root of both sides, which gives me the square root of x minus 5 over 3 equals y. But don't forget, when you take a square root, there are two solutions, a positive and a negative. So, in this case, one of these is the answer. It's either positive or the negative. And the trick is, this component tells you which one, if you're willing to use it. So now I'm going to graph my original expression. Let's do it. I'm going to use this one. It says my original expression was 3x squared plus 5. So 3x squared plus 5. So notice that this one is to the left of 0, so that's from negative infinity to 0. Okay, now look at my possible inverses. I have the positive square root of x minus 5 over 3, which you notice is over here. Notice that does not look like it matches, right? And I can verify that by just picking some points and see if they work, right? Here I have the point negative 1, 8, but I don't have the point 8, negative 1. Remember, I should always have that opposite relationship of each other. And so these are not inverses. Well, what about the negative? Well, that looks like an inverse. And so for this problem, f inverse is the negative square root of x minus 5 over 3. You have to be conscious when you do these problems of the fact that there could be domain issues or there could be issues with the radical. And so you must always be on point and looking and trying to find places where this can happen. And these are most common when dealing with even powers and roots. Now, if you start with the even power, you often have to use the vertex to restrict the domain. If you start with the root, what you're going to run into is you have to choose the positive or the negative. And you should always end up with that choice if you do it correctly. There's just no way to get around it. Now, the only other thing I have to tell you for tonight, and this is not necessarily a notes thing, the only other thing I have to tell you is there'll be some problems that are going to test your algebra skills. And so let's look at some of those to finish out with. There's some great examples of these in the text. For the ones that involve the radicals, I would strongly recommend looking at example 3 and example 4. Those are pretty helpful. Okay. Now I want to look at number 22. These are ones where there's not a radical or an even power, but the function itself is weird. So we have f of x is equal to 2 over x plus 8. Okay, let's take a look. So first thing, in this function, one of the big things that I can do here is whenever I look at this function, I can follow the same steps as before, but eventually I'm going to get in a spot where it's going to be weird. So step 1, I'm going to write this as y equals 2 over x plus 8. Step 2, I'm going to swap around x and y, meaning this is now x equals 2 over y plus 8. But now we get to step 3. How do we solve for y? Well, the trick is, I'm going to, for this kind of problem, cross multiply. What does that mean? Remember, this is x over 1 equals 2 over y plus 8. There is no way to get around this problem. You will always end up cross multiplying. And 24, which is the next one we're going to do, is going to follow the same basic procedure. So don't think you're going to get out of it just by trying a different method. Okay, let's do it. So when we cross multiply, remember you're going to take x times y plus 8 and 1 times 2. So we take x times y plus 8 and 1 times 2. Now x times y plus 8 would be xy plus 8x. And 1 times 2 would, of course, be 2. So we just took our function and we simplified. Now, once we simplified, we're going to attempt to solve for y. Well, how do I get y by itself? I'm going to start by moving the 8x over. That would give me xy equals 2 minus 8x. And then I am actually going to divide both sides by x. Because what's that going to do? The x's on the left side are going to cancel, leaving just y by itself. On the right hand side, we end up with 2 minus 8x over x. You can leave it right there, which means that f inverse for this function is 2 minus 8x over x. This is a common thing with things like number 22. Let's take a look at our graph. Verify that these are in fact inverses of each other. Let's get rid of all these. I want to make sure I get y equals x. That's going to be my middle one. Okay, let's do it. My original one was y equals 2 divided by x plus 8. My inverse is y equals 2 minus 8x over x. Wow, this is a little bit more difficult to see, but these are inverses, right? I mean, this purple graph, if I pick any point on it, like this one, negative 6, 1, then on the black graph, there should be the point 1, negative 6, which if you go over here to 1, go down to negative 6, 1, there it is, there. So you got 1, negative 6, and negative 6, 1. And over here, we've got negative 7, 2, and we got 2, negative 7 right there. Take a little bit. Come on, mouse. There we go. Close. You saw it. And notice that the original function here in purple passes the horizontal line test, because while this one keeps going to the left, it always stays below the axis. It always stays below. And this one always stays above. So there's no crossover. There's no failing the horizontal line test. And our other one also passes the horizontal line test in a different place, but it does. And when you put them both together, these are very much reflected across this green line. And so these are inverses. For ones like 28, which is the next one we're going to do, or sorry, not 20, 24, it's the same basic process. You'll find that this happens quite a bit. It's just how the functions work. So make sure you're noting how they fit together. Let's go ahead and take a look there. And that'll be our last problem. So let's look at 24. 24 states we have f of x is equal to x plus 3 over x plus 7. All right, well, how do we do it? Step 1. Y equals x plus 3 over x plus 7. Next, step 2. Everywhere there used to be an x, we're going to replace with y. So y plus 3 over y plus 7. Everywhere there used to be a y, we're going to replace with x. All right, step 3. We're going to cross multiply by writing this as x over 1 equals y plus 3 over y plus 7. We're going to cross multiply, and this will give us our new equation. When we cross multiply, we take x times y plus 7 and 1 times y plus 3. Now, we're going to simplify by distribution. This one has some quirks to it, so that's why I wanted to make sure to go through one like it. Let's take a look. When I distribute, I get x, y plus 7x. So the x times the y gives me xy, x times 7 gives me 7x, 1 times y gives me y, 1 times 3 gives me 3. Now, what I need to do is get both y's on the same side. Okay, meaning what I'm going to do is I'm going to subtract y to move it over here, and I'm going to just subtract 7x to move it over here. What does this look like? I have x, y minus y equals, the 3 didn't move, so it's still a 3, but I did subtract 7x from it. And so I get this equation instead. Notice the y is now a negative y on the other side. The positive 7x is now a negative 7x on the other side. Now, what we do is we factor y. So I take a y out of everything on this side. You have to do this step. So y times x. Now, when I take a y out of this one, I'm going to be left with a minus sign and a 1. Last thing, I want to make sure to get y by itself. How do I get y by itself? I'm going to divide. Remember, I can add and subtract, multiply, and divide to both sides. And in this case, I'm going to divide by x minus 1 on both sides. So I get y by itself equal to 3 minus 7x over x minus 1, which means that my inverse function is equal to 3 minus 7x over x minus 1. Let's verify. I got a graph. Let's do it. The big tricks in this one were to make sure, as we're doing it, to note, you have to make sure to cross multiply correctly and distribute correctly. Then you want to get all the y's onto one side and everything that you can move to the other side. We then factor a y out of everything and then divide to get y by itself. Standard algebraic rules there. So in the first one, I end up with, let's see, it was x plus 3 over x plus 7. So on top, I have x plus 3. On bottom, I have x plus 7. Okay. And on the second one, I have 3 minus 7x over x minus 1. Look at that. It's cool looking, but it's an inverse, right? Because if I come over here and I look at the point in the black one, it says, oh, is there an easier point? That's not a nice point. Not really. Right here. 0, negative 3. And in the purple, I have 3, negative 0, opposites. If I come over here, in the purple, I have negative 9 and 3, which means over here I should have 3, negative 9, right there. Boom. And so these are, in fact, inverse functions, and they are, in fact, split by this green line. If you tilt your head, it looks kind of artistic. I don't know. I don't do much art, so. You can see here we have this intercept up here of 0, 0.429, and then on the black one we have 0.490. And so, yeah, they're definitely inverses because they match the properties. And so there you go. Cool. That'll be it for today. 1 hour. Oof, it was a long one. Let's remind ourselves of our homework assignment. Oh my gosh, I didn't post it first thing like I normally do. Whatever will you guys do? I don't know if you guys can handle that. Okay. Homework assignment. Oh my gosh, how terrible of me. How rude. The homework assignment was page 444/462, 5 through 45 odds. There we go. That'll be it. Hope you guys have a good rest of the day. You might notice that section 5.7 is, in fact, the last section of the chapter. I wonder what that means. I'll see you guys next time. Bye.